Today we're going to take a look at exponential functions. So when you say something grows exponentially, you're going to have just a little bit more understanding of what that means after this section. So first of all, what is an exponential function? Well, first of all, we say that it has base b, b for base, and exponent x. So we want b to be a positive constant number other than 1. The reason why it can't be 1 is because if I have 1 to the anything, it comes out to be 1, because 1 squared is 1, 1 cubed is 1, 1 to the 4th is 1. So 1 to the anything is 1. So we can't have 1 as our base. But any other positive constant number. Notice when I say constant, that means that it could be 1/2, it could be 38, it could be 5 million, as long as it's positive and it doesn't have a variable involved. It can be our p-value, okay? Now, x can be any real number. It can be positive, it can be negative, it can be whatever we want it to be. Now, let's say I want to evaluate our exponential function. So in this case, I have f of x equals 42.2 times 1.56 to the x. And it's modeling the average amount spent in dollars at a shopping mall after X hours. And they want to find out what is the average amount spent to the nearest dollar, so no cents, no pennies, no quarters, anything like that, to the nearest dollar after 3 hours at a shopping mall. Note that they say 3 hours, and they're saying hours is our X, okay? So, given that information, we're going to substitute 3 in for the x. So we have, note that this is f of x. Now we have f of 3. Don't forget to change this to a 3. Okay, that is important to do. And that means you're replacing this with 3. Okay, so you should have your graphing calculators out right now. I'm going to pull mine up as well. And you should practice typing in 42.2 times 1.56 to the third. Okay, and you're welcome to type it with the parentheses instead of doing the time symbol. Both are going to give you the same answer. Okay, but you need to be able to practice typing that in, so make sure you do that. All right, you'll notice that when it says round to the nearest dollar, okay, that's why we say it's approximately 160. Keep in mind, since this is a word problem, I would expect you to answer this in sentence format. So, after 3 hours at a shopping mall, the average amount spent is $160. Now, let's say I want to graph an exponential function. Well, the key here is to make sure that we choose an appropriate t-chart. So, I'm going to pick -2, -1, 0, and 1 for my x values. Okay. I would probably also include 2. So I'll show you how that works in just a moment. But when you plug in -2 to this spot right here, you get 3 to the -2. Remember that when you have a negative exponent, it moves it to the denominator. So 3 to the -2 is really 1 over 3 squared, which comes out to 1/9. Okay, and 3 to the -1 is 1/3. 3 to the 0, anything to the 0 power is 1. 3 to the 1 is 3. And then let's say I want to plug in 2. Well, f of 2 equals 3 squared, which is 9. Okay, so most of the time what you do is you would see this as a t-chart. So you'd have like your x and your y. Okay, you have -2, -1, 0, 1, 2. And then you'd have 1/9, 1/3, 1, 3, and 9, like that. So that's probably how you would write this. But once you plot those points, okay, and you'll notice that 1/9 is really close to 0, but you do want to make sure that's above it, and 1/3 is slightly less than half. Okay, once you plot those points, and again, you'll notice here they didn't plot 2, 9 just because they didn't want to graph all the way up here. That's why they did do that one. You'll be able to connect these in one smooth, continuous curve. and you draw your arrows at the ends. And hopefully you can see that I have something special going on right here. And that's because that's a horizontal asymptote. Horizontal asymptotes, exponential functions, hand in hand. All right. So our standard horizontal asymptote is at y equals 0 for an exponential function. So we take that into account when we do shifts. So if I have any vertical shifts, I will also move my horizontal asymptote. So looking at this is the shift that they give me for 3 to the x minus 1, a horizontal shift or a vertical shift. So this one's a horizontal shift to the right 1. So in this case, you're going to notice that we have these 3 points. We're going to, first of all, apparently label them. Forgot I had that. Okay. And then we are going to shift that, okay? So literally, I'm taking my negative 1 1/3, and I'm adding 1 to the x value. So my x was negative 1. Now it's 0. Then I have 0, 1. I'm going to add 1 to the 0, which is the x value, and now it's 1, 1. And then I repeat with 1, 3, and it becomes 2, 3. And you're going to notice that the horizontal asymptote, because it's this way, and I shifted this way, it doesn't change the equation of that line. So it is still y equals 0. So it's going to be y equals 0 unless there's a vertical shift, okay? So again, notice that I'm shifting to the right 1, I'm shifting right 1, and right 1. That's all that's happening here. Now, you will absolutely need to pause this video to get all this in, but I'm going to highlight some things for you, literally. Highlight. Okay. The domain of an exponential function is negative infinity to infinity, and the range for a standard one is 0 to infinity. Notice that if you have a vertical shift, your range will change. Okay. All things of the point b to the x pass through 0, 1, because b to the 0 will always be 1. All right, and then if b is greater than 1, then we have an increasing function. Okay, so in this case, that's the blue one. Okay, if you look over here, we have a blue curve is increasing. B is greater than 1. And if b is between 0 and 1, then it's a decreasing function. Okay, so it gets smaller as you move along. Now, these are also going to be one-to-one functions. That means that you can find their inverse. And they have a horizontal asymptote at y equals 0. Okay, so horizontal asymptote at y equals 0 is also super duper important. All right, so feel free to pause this video to capture all this. And when you're ready, come back and press play. Now, E is a very special number, okay? It is the value of 1 plus 1 over n raised to the n as n gets closer and closer to infinity. What in the world do I mean by that? Well, if we were to pull up our graphing calculator again, and we go to our y equals, and we type in 1 plus 1 over x raised to the x, like that. And we're going to go look at our table. Okay. As x gets bigger and bigger and bigger, so I'm scrolling down as x gets bigger and bigger. What you're going to notice is my y is also getting bigger, but not very quickly. Now I'm going to go look at my table settings. You'll notice it says table set here. And I'm going to go ahead and make my table count by something a little bigger. I'm going to count by thousands. So now when I go to my table, you'll see I'm counting by thousands. What do you notice happens to my y as my x gets bigger and bigger? Hopefully you say it gets to be pretty much the same number all the way. Now, it's actually going to have bigger digit or more digits as we go along, but as we get closer and closer to infinity, and we move further and further in the table, this limit gets closer and closer to this number here. We call that e. Okay, it is irrational because it goes on and on forever without repetition. It's very much like pi in the sense that you can never find all the digits. For your purposes, you can probably know that it's about 2.7. All right. Now, it's called the natural base or the natural number. And if we have e to the x, then we can call that the natural exponential function. And that's because this happens naturally in nature a lot. That's one of the reasons why we call it that. Now, let's say that I have this exponential function, f of x equals 1066 e to the 0.042x, and it models the gray wolf population of the Western Great Lakes, X years after 1978. Project the gray wolf's population in the recovery area in 2012. Okay, so at this point, you need to decide what X value you have to plug in. So if we started in 1978 and we're looking at 2012, then when we subtract 2012 and 1978, we get that. That's 34 years later. All right, so we are looking at x equals 34. Again, we did 2012 minus 1978 to get that 34. Now, that is what we need to plug in, and I'm going to show you on our calculator how we do that. So if you go to your main screen, so you go second quit, like that, you're going to see right here it has ln, and on mine it's in yellow. It says e to the x. So I'm going to go 1066, and then I have to click my second button, and then my e to the 0.042, and instead of x, I'm plugging in 34. Okay, I'm going to also show you that on the Casio, where that button is. So you see here it says ln. That's the key again. Okay, so you type in 1066, and then you have to press shift e to the parentheses 0.042 times 34. So what you're going to notice here was that on the TI, it automatically put in the parentheses, whereas on the Casio, you have to fill them in yourself. The parentheses are required. Okay, so again, E is in yellow here and here, depending on your calculator. Now, I plugged it in, and I got approximately 4,446. Now, you'll notice that this didn't tell you to round to the nearest whole number, but given the context of the problem, it makes sense to do a whole number, because this indicates that the gray wolf population in the Western Great Lakes in the year 2012 is projected to be approximately 4,446 wolves. Okay, so keep in mind that we're saying wolves means we need whole numbers. We generally don't have 4,455.6 wolves. Okay, so that's the key here, is we're definitely wanting to round what's appropriate for the problem. Now, one of the things I really like about exponential functions is how they relate to money. I like earning money. You know, interest is really a wonderful thing. You have enough money in a savings account or a CD or in stocks, whatever. You're going to be able to accrue a pretty hefty amount of interest. So this is the formula here for, let's call it normal compounding, periods in a year. So if it's annually, n equals 1, because it happens once per year. If it's monthly, then it compounds 12 times in a year. If it's weekly, it's 52 times in a year. So you pick the n value based off of however many times it tells you you're compounding. You can compound weekly, daily, hourly, by the minute, by the second. And the smaller and smaller and smaller your unit is, how often you're compounding, okay, gets more and more often, then the closer you are to compounding continuously. Compounding continuously means every moment of every single day it is compounding. Reminder how compound interest works. The idea is that you earn interest on the original amount. Then that amount changes because you've added interest. Now you're earning interest on the new amount. Then that interest is added. Then you earn interest on that new amount, and so on and so forth. So it snowballs. Okay? So these are the two formulas that you need to know. Because let's say you have $10,000 and you're investing it at an annual rate of 8%, and it is compounding quarterly. And you want to figure out how much you have after 5 years. Okay, well, first of all, 8% means that R equals 0.08. You will have to turn that into a decimal. Okay? $10,000 is your initial amount, or your principal. So we call that P. Okay? 5 years, that's our T. Time will always be in years. Okay? And it's subject to quarterly compounding. How many quarters do you have in a year? Well, that's going to be 4. So N equals 4, and we're going to be able to plug in. Again, P, we're going to plug in 10,000. R, we're going to plug in 0.08. N is 4, and T is 5. So this is 4 times 5 in the exponent there. Now, calculating this, again, you want to practice typing this in your calculator. Again, if you're sitting there just watching me do this, you need to make sure you pause the video, go find your calculator, pull it out. Very important to be practicing the typing. So I have 10,000 times 1 plus 0.08 divided by 4 raised to the 4 times 5. Or you can just type 20 if you prefer. Okay? And that's how you have to type this. Again, pay attention to the parentheses. So after 5 years, if you invested $10,000 and you have 8% compounding quarterly, you're going to have a total of $14,859.47. That means you got almost $5,000 in interest just by investing this somewhere with 8% interest rate. Okay, so make sure you write your answer as a sentence for these. Don't forget that. Now, do you think it would be better to compound quarterly or compound continuously if you are saving the money yourself? Well, let's find out. So let's find the balancing account if we're compounding continuously. So instead of the equation with the N in it, we're going to do the equation with the E in it. So we plug in 10,000 for P, 0.08 for R, and 5 for T still. So all of that is still the same. But now in our calculator, we do 10,000 times, and we are going to have our E to the 0.08 times 5. Notice I have to type my E from here again. And you'll notice that I get $14,918.25. So I am earning a little bit more money by compounding continuously for 5 years than I did at 8% compounded quarterly for 5 years. It's good to know. Now, let's do some practice. Pause the video and try these. So 6 to the negative 1.4. And if you're getting an error, okay, so really quickly, let me show you the error. If you get this error that says error syntax, and you go to, it's going to highlight that minus sign. That's because that's subtraction. So just in case that's happening to you, you need to go back and make it a negative sign. This one right here. You see it's much smaller. Okay, and you get 0.08. 139, blah, 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 blah. Okay, so I'm going to say 3 decimal places for these. So 0.081. Okay, and for e to the negative 0.82, you're going to do e to the negative 0.82. Oh, don't know how that happened. Let's fix that. All right, there we go. And we get 0.440 if we round it to the nearest 3 decimal places. Now, graphing 2 to the x using, let's say, -2 to 2 as your x values. Create a t-chart, plot the points, and draw your graph. Okay, so I'm going to use -2 to 2. So f of -2 is 2 to the -2 is 1 over 2 squared is 1/4. Don't forget, these should be fractions over here in the y side, okay? F of -1 is 2 to the -1, which is 1 over 2, which is 1/2. F of 0 is 2 to the 0. Anything raised to the 0 is 1. Now, when I plug in 1, I get 2 to the 1. When I plug in 2, I get 2 squared, which is 4. Okay? So I mostly show the work for these ones because the fractions start to get a little sketchy if you don't write them down. So I have -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. If you wanted to do 3, 3 would end up being 8, just for your reference. All right, and we know we have a horizontal asymptote at y equals 0 that we're having to follow here. By the way, it would be a really good idea to have a colored pencil for the asymptotes when you draw them. Otherwise, you might get totally confused because they'll blend in with the x-axis. All right, so we're going to curve with the asymptote. You can't draw it very far or else it blends. And then we put arrows on the end. Ta-da! All right, try finding this, in this situation, compounded semi-annually, which is n equals 2, compounded quarterly, n equals 4, compounded monthly, which is n equals 12, and then compounded continuously uses the E equation. Then press play. So I'm doing this in my calculator right now, and I get that semi-annually would be $23,881.05. If I change it to quarterly, then I get $23,912.36. If I do this, what's the next one? Monthly, then I get $23,933.61. And then last but not least, if I did it continuously, so we're compounding 6% for 3 years, I get $23,944.35. If you did not get those numbers, you need to try typing them in again. Take a look at someone else's calculator around you to double check how you're typing. Great work today. Exponential functions in the books.